didn't have a chance last week to see Stockholm if they wanted to see something. I have a suggestion now. What you could do, apparently, the new Salvador Dali exhibition opened, the Modern Museum, Modern Art Museum. Apparently, it is very good. And then on Friday we have some program is a little bit different to the old one. So you might want to have a look at that, because now Bennett is going to give his real talk on Friday. So today is the warm-up, and he needs to take a little break, go away and sort of think about the criticism he gets today, and we'll fix it all on Friday. So I'll leave it to the kids.
Well, good morning, and thanks to Lars and Nils for organizing such a nice workshop in this beautiful place. This picture is for Anna. This is my neighborhood, and Anna was in the neighborhood a few weeks ago and didn't even call me.
6 in the morning, 6.
So today I'm going to give a very pedagogical talk about the dynamics of the distinct superfluids in a neutron star. So we believe that we have a neutron superfluid in the inner crust, and then a separate 3p2 superfluid in the outer core and a superconductor. But I'm going to focus primarily on the dynamics of the superfluid in the inner crust, simply because it's a one-component superfluid and easier to talk about and think about. And I think by now we all understand what motivates this sort of question, why we should worry about superfluid rotational dynamics. There are a number of modes in neutron stars and phenomena that we would like to explain and understand. There are the crust shear modes excited in magnetaric flares, as were discussed by Anna and Yuri and by Martin. The spin jumps or glitches, over 100 have been now observed in the pulsar population, which Kostas will be talking about. And then there are the stochastic spin variations or timing noise that there's been little discussion of in this meeting, but I think that's a very interesting subject. And then finally, there's what appears to be precession or wobble or nutation that's been seen in a handful of neutron stars, which I will return to as an example late in the talk, as an example of how the coupling of the superfluid to the crust can determine the frequencies of these modes. As moderator, I decided that less is probably more in this case. This would be low level of absolutely no value to the people that have thought about these problems, such as Lars and Nils. So I think I'll only devote an hour to the first point, vortex dynamics and pinning, the subject of the talk, connection to superfluid dynamics. And then in the second hour, I'll show you some calculations indicating that vortex pinning should be inevitable, at least in the inner crust, and I'll argue also in the outer core. And in the third and fourth hours, I'll talk about the relevance to neutron star modes. There won't be time for lunch, I'm sorry, and then I think we'll have to cancel the rest of the talks and go to dinner. So starting with the first one, vortex dynamics and pinning. The way a superfluid rotates is by establishing an array along the rotation axis of quantized vortex lines about which there's a flow and within which superfluidity is destroyed. So you have a core of microscopic dimensions separately, a core of microscopic dimensions typically, and these vortices are separated from the other vortices by some mesoscopic scale. In the case of a neutron star, say 1/10 of a millimeter for a typical spin rate. And the number of vortices is determined by the rotation rate of the container. Here are some pictures in rotating superfluid helium where we're looking down the rotation axis. So these dots indicate the vortices. These are photographs, actually. And this is a critical rotation speed is reached and a vortex is nucleated. You spin a little faster, a second vortex is nucleated. And then you get more and more, and then a triangular array of vortices is established. Here's a very nice picture of vortices in a trap Bose-Einstein compensated, different rotation rates. And so the distribution of these vortices determine the fluid's angular momentum because they contribute a net flow, an average flow, which is approximately that of a rigid body. And for a typical neutron star spin rate, we have about 10 to the 17 neutron vortices in the object. Just a few simple considerations about vorticity and fluid flow. This is true whether you're talking about an ordinary fluid or a superfluid. Let's define vorticity in the usual way as the curl of the flow velocity. And then if we have some local vorticity, and there's flow around that that creates the vorticity, and we consider some line that encloses an area about which there's the flow, the circulation is defined as the line integral about that. And then that is equal to, through Stokes' theorem, to the vorticity that punctures that surface that's enclosed by the line. In a rotating superfluid, we have now the vorticity is in well-defined persistent structures, the vortex line, and about each vortex line carries one quantum of circulation, one quantum of vorticity. So this line integral about a vortex gives the same value for each vortex line, and so then if you put this at the origin and solve for what the flow is, you find a velocity field around the vortex that's azimuthal around the vortex, diverges as 1 over r until you reach, at microscopic dimensions, a normal core, normal neutrons. Now if you take many of these and you puncture the surface, some surface with these convex-vortex lines, and I'm saying that each vortex carries kappa vorticity in a delta function, just for illustration here. And so the net vorticity now is just the sum over all of these vortex lines. The same considerations apply. We can calculate the circulation, and that'll be determined by the number of vortices that puncture this surface times how much vorticity each one carries. So it's kappa times the number of vortices enclosed, and that's true no matter what I do with the vortex arrangement here. I can move these around within this line. What matters in determining the vorticity is simply how many lines puncture that surface. It works like Ampere's law. And so, if I want to change this circulation, the only way to do it is to change the number of lines that are enclosed. That is to simply add lines here, puncturing the surface, or take lines out. For those who prefer to see this in terms of conservation laws, this is the way I like to think of it. Let's consider a single component superfluid. It obeys Euler's equation. We can have some other conservative forces in the problem, some chemical potential and a gravitational potential, and let's add in a non-conservative force density. And then we'll have equations also for the normal component. The equations of motion for the superfluid vorticity can be obtained just by taking the curl of this, and that gets rid of the grad terms. And what we get is this evolution equation for the vorticity that depends on the curl of the superfluid velocity crossed into the vorticity plus this non-conservative force that we're applying. And the thing in parentheses, turns out, is simply the local vortex line velocity cross product with the vorticity, which can be seen through the following argument. Suppose we take these vortices that are puncturing the surface and we started vecting them out. And we take the time derivative of the amount of vorticity that's puncturing this surface. Well, the flux of vortices coming out of this surface will be the vortex velocity crossed into the vorticity dotted into some little element of line about this surface. And then if you use Stokes' theorem once again, you see that what is in parentheses must be that. So we can make the identification that the vortex velocity crossed into the vorticity is the superfluid velocity crossed into the vorticity plus this non-conservative force that we're applying. Or just reorganized it to write it this way, we get this result, which I like because it's a good way to see how vortex motion is determined by the dissipated forces in the problem. So if we have no force, we turn off the force, then the vortices will always move with the local superfluid. Nothing very interesting happens. On the other hand, if there is a difference between the vortex velocity and the superfluid velocity, that implies the existence of a force, or if we have a force per unit volume, that drives the vortices to move relative to the superfluid. But minus that force, by conservation of momentum, is the force that's exerted on the normal fluid. So it's through this force that the superfluid and the normal components talk to one another. And so that's why the dynamics of the superfluid needs to be solved for self-consistently along with the dynamics of the crust to get any kind of mode that you would like to understand. at this level, let me remark that really everything I've said holds for an ordinary fluid. It's just that because we have quantized vorticity and persistent structures, each carrying the same quantum of vorticity, these things don't decay through dissipation like in a normal fluid. It's convenient at times to talk about the dynamics of the fluid in terms of what individual vortices or bundles of vortices in a fluid element are doing. And that's the point of view that I'll take through the rest of the talk.
Can I just ask, you say this is only the sort of frictional forces that are measuring here? What about density gradients and whatnot? Because generally, there will be a force on the vortex due to the fact that its density depends on, its energy depends on the density locally. And so that will be trying to push things to lower densities as a rule. And what I don't see here is those sorts of effects. How did they get removed?
The force I'm talking about here is any component of the force that's not described by potential, so that has a finite curl. So when we were back here, we had these guys. Are these the guys you mean? Our chemical potentials? So here really what I'm talking about is a force that has a finite curl. I guess I don't understand your question very well.
Is the effect that's trying to push vortices to, well, if I don't worry about how gaps depend on density, that wants to push vortices to lower densities.
It is not included here. It is assumed that such things are compensated by, well, general hydrostatic equilibrium. But it might be present actually in the equations.
Because these sorts of things distort the lattice, for example. Okay, we can talk about this later on.
I think, since I didn't tell you what F is, I think what you're talking about could in principle be incorporated.
Well, except you say it's non-conservative, but I was...
Yeah, there are conservative pieces in there. But, so what the questions you wrote is the force balance for one vortex. I mean, this is Magnus force equals something else, right? So.
Well, no, I haven't restricted myself to one vortex here. This is all talking about average quantities when I made this identification. So I'm just talking about a superfluid velocity. I haven't said anything about the vortex, about individual vortices, though I have defined an average vortex motion.
Yeah, but this is the force balance for a single vortex as well.
Yeah,
so
sure, absolutely.
The terms Chris is looking for are encoded in F.
Yeah.
But okay, you derive them if you take the total stress tensor close to a vortex, and then the terms Chris is looking for, they're coming from variation along the vortex, variation of the background density and chemical potential.
So I think the answer to Chris's question is they can still be put here.
Yeah, there is that.
So just to summarize some of the things I've been saying is that the point of view I'm taking is that the vortex mobility with respect to the superfluid is related to forces that are exerted on the fluid and therefore exerted back on the normal component. This vortex mobility will in general be determined by the microphysics. We'll talk about that a little later. And all of this together determines the forces on the solid whose spin rate we observe, and so couples to determines the features of the properties of the hydrodynamic modes of the star. And we expect vortices to pin. One place where they should pin, as we'll hear from Francisco later, is to nuclei in the inner crust. Another place they could pin is to flux tubes in the outer core. And the relevance of pinning is this, that if we have some number of vortices that puncture this surface, the circulation is conserved if the number within this surface stays the same. That is, if we immobilize them and don't allow them to move out, the superfluid velocity will be locally fixed. And in the case of a uniform distribution of vortices, that is a constant number of vortices per unit area then locally, the superfluid velocity is proportional to the areal density of vortices. And so, to the extent that that areal density is fixed by pinning, the superfluid angular momentum will be fixed. So to understand the flow of angular momentum, we need to understand how the vortices move, and to change the angular momentum, we need to move the vortices.
But I think the photograph you showed of liquid helium, you see that suddenly there's one vortex, and two, then three. So how do they appear? They just suddenly form in the middle of the superfluid, or they come from the boundary?
My understanding is they tend to nucleate at the center.
Yeah, but then you have zero, then you have one, two. So why in this case could you just disappear a vortex?
In which case,
Here, in the neutron star. Looks like it was happening in helium, no?
in which situation? Make them disappear when? What do you?
When you increase the spin rate of the helium pocket, and suddenly there's one vortex, no? Then suddenly you get two. How do they form? They just suddenly appear in the middle of the liquid, or they come?
They
Understand you kind of create and destroy, but if you have one and you go to two, you have to create one.
nucleate somewhere.
At the boundary, and then
They come from boundary and then they immediately
yeah,
move to
but,
Right.
but they don't, the photos don't sort of track the dynamics of this
Yeah,
process.
uh-huh.
Suddenly you have five, so I think they have to nucleate on the boundary.
And so in that picture,
If we're just cooling it down, then
Oh yeah, but if you then you start with the rotating sample and you cool it down. But here you sort of take the superfluid sample and you spin it up by
yeah.
essentially rotating the boundary somehow. Then they have to nucleate on the boundary.
and so in the pictures you saw, they were pretty much uniformly distributed
after
in equilibrium energy.
So Daniel's question is, why can't you nucleate vortices in a neutron star? Or why can't they disappear
Well, I
spontaneously?
think you will if you spin up a neutron star at
Yeah, but also in the boundary.
the boundary.
Yeah, but I mean, most of them will be made just in the cooler, right? They'll be made in situ. They'll have rotating.
Yes.
No, that's
Right.
But,
Yeah.
um,
And then then as it spins down, they migrate outwards and get destroyed at the boundary.
unless
Yeah.
you have an accreting star that spins up. So the formation of a millisecond pulsar that is
Yeah, okay.
recycled, then you
Right,
have to spin it back up,
Yeah.
and then you have to nucleate. So I think there's something we don't discuss enough, is how the vortices are destroyed when you get out to the whatever the boundary is, and how they nucleate. It's kind of could be interesting.
It always have to be the boundary. There is no way to create one in the middle, so.
Well, according to the
Topologically, it's
exactly. So I
The
think
photograph looks different, so I think, okay, it's something.
Yeah, so I think there's several ingredients that are coming. As Chris mentioned, it starts at a large spin rate, it condenses, and it establishes a vortex array that's fairly dense. The star spins down. The superfluid, if it's to lose angular momentum, we migrate vortices out towards the boundaries where things turn normal and we're destroyed. It just goes to normal.
they just, gently fade out.
Yeah. They get fat.
Sizes get
Right,
big,
they get
Yeah.
fat and they join to the normal region. Then, if we've spun them up, we're spinning them up, say in a millisecond pulsar, we have to make new vortices, so they do nucleate in some way in the normal regions. So those, I suppose, would tend to be near the outside, but could, in principle, I suppose, be, if we have a region, say near the crust core boundary where we have S-wave superfluidity and P-wave superfluidity, maybe we have a normal region there. It could be a nucleation region.
This vortex to move out and out, they got to the boundary of the superfluid, and sometimes you will accumulate there, no? And then suddenly
No,
they
they're
fuse and
they're gone. They're gone. You're pushing them into normal regions. They
Well, it's
disappear.
not, I think, I did think about this at some point, and I got confused, but I think what Chris is sort of saying, what I was thinking, that basically the coherence length increases
Yeah.
as you go closer to the critical temperature. They get fatter and fatter,
Yeah.
and at some point they start overlapping, and you essentially have
Yeah.
normal vorticity. But there's an interesting question, that if you push all the vorticity out, usual sort of hand-waving, this is how, say, glitches work. You just say, oh, it all just is global. Right? But this says that you actually translate all the angular momentum that you're changing to, there's something happening at those boundaries. Exactly, and those boundaries of the sphere will be sort of in the equatorial plane, essentially.
But the angular momentum
That's-
transfer
and
occurs
so that-
before. If we're to migrate the vortices at all, if we're to move them outward from the rotation axis. There has to be a force on the vortices to do that.
And there has to be
And so there's a torque on the crust. And so the angular momentum transfer is occurring there as the vortices are moving outwards. If there are no forces in the problem, then they just co-rotate with the superfluid essentially forever. And there's no loss of angular momentum. So the loss of angular momentum amounts to moving the vortices outward, but that requires motion with respect to the superfluid, so there has to be a force. So there are torques. And that's how the angular momentum is changed.
How do you get to this uniform density state? If the vortices are pinned and they're made near the edges?
We may not. We may not. This is a pedagogical talk. Everything is uniform.
The same way your lattices are built up, right? The same way.
I think it's also important that the lattice is not quite uniform
Yeah, I don't
because of
think
these density gradients.
Yep. Of course it's
this
not
effect
uniform.
has been seen in the coal gas experiments.
It's probably not uniform or nicely rectilinear as I've drawn. Consider this to be some small region of the star where we're asking what the vorticity is. I wanted to say a few words about how pinning might occur. We'll hear, I think, from Francisco at 7 o'clock tonight, when I'm done, how this works, is that if you have a vortex next to a nucleus and you compare the energy of that configuration to having the two superimposed, the second situation, at least for some densities, lowers the energy because of the density dependence of the gap. So very roughly speaking, the nucleus is somewhat less superfluid than the ambient medium. The vortex core is normal, a price it paid to lower the overall energy of the system. So if you take a nucleus and put it onto a vortex that has already paid that price of destroying the neutron superfluidity, you can lower the energy. So we'll hear about those calculations, but the typical numbers that come out is that there's about an MeV energy gain per nucleus of this superposition. So there's a force between a vortex line and a nucleus that tends to make the vortex be on top of the nucleus. Another place they're expected to pin is in the outer core. Here we think we have a type 2 superconductor where there are flux tubes, and these are magnetized to fields of about 10 to the 15 Gauss. And then we have vortex lines, but in the core, because of entrainment, the neutron circulation also implies a proton circulation, which magnetizes the vortex in the core up to about 10 to the 14 Gauss. So now, if you want to change the angular velocity of the superfluid in the core by moving vortices, you run into flux tubes, and you pay the magnetic energy cost of that overlap. And that energy, that interaction energy, will be approximately the field with the flux tube times the field with the vortex line times some overlap volume, and that's been estimated to be about 5 MeV per intersection. So the effects of pinning are they could produce glitches through some instability, and angular momentum can be stored as the star spins down. The vortices are pinned to, say, nuclei or to flux tubes in the outer crust. The angular momentum is fixed. The crust continues to spin down, and now the superfluid acts as an angular momentum reservoir. Then, through some sort of instability, at least in principle, the vortices are made to unpin, and then angular momentum gets transferred to the crust and spins it up. And that's the idea that's been around for quite a while. But what I want to focus on mostly is how pinning will affect superfluid modes, and a particular example I'll use is precession modes or wobble modes, neutron stars, which seem to have been observed in several cases. On to the second part of my talk, I'd like to argue that vortex pinning is inevitable, at least in the inner crust. And my conclusions are based on looking at the forces that determine vortex motion. I already talked about this basic interaction of about an MeV between a vortex segment and a nucleus. A vortex also has a very large self-energy or tension that is due to the kinetic energy in the flow of the superfluid neutrons about the vortex core. So we have this quantized circulation, which implies this velocity field. And if you integrate up how much kinetic energy per unit length along the vortex line there is, it amounts to about 10 MeV per Fermi. This means that it's very hard to bend a vortex line because it changes the velocity field and increases the energy. It's an energy cost for bending it. So the vortex lines in some sense are very stiff and hard to bend. Another force that acts on a vortex is the notorious Magnus force. And on a vortex that is moving, or with respect to the superfluid flow, or has the ambient superfluid flow, we have an ambient superfluid flow past the vortex. So now looking down the axis of a vortex, so it's circulating in this way. The neutrons are circulating this way. And so suppose we impose a local superfluid flow that's essentially the vector sum of the flow of all of the other vortices in the system, creating this ambient flow. And then if we think for a moment if this is an incompressible fluid, and by Bernoulli's law on this side of the vortex, these velocity vectors add constructively, so we have a reduction in the pressure. On this side, the reverse is true, and we have an increase in the pressure, and so I guess I got my force vector wrong. Magnus force should be up this way, but it's orthogonal to the direction of the global flow. And finally, there should be a dissipation force associated with irreversible energy transfer of the vortex as it's forced to move with respect to the lattice nuclei. So just a picture of that. The vortex motion will couple to phonons, the lattice phonons that is, but in principle to any other excitations in the system that we can think of. So as the vortex moves along, it wiggles, and excitations appear in the form of waves on this vortex line. And as it moves along, because of this vortex-nucleus interaction, it effectively plucks the nucleus away from its preferred location in the lattice, and that excites waves that propagate through the lattice and lead to dissipation or drag on the vortex. So the dynamics of this problem of how does a single vortex move through the lattice can be addressed in continuum mechanics by thinking of the vortex as a line with tension that obeys the appropriate equations of motion for an object with vorticity. And those equations look something like this. U is the vector displacement. So I should have drawn a picture that if we have some distribution of nuclei, and we have a vortex, which I'm now treating as a string, and we establish a coordinate system, x, y, z, then with this vector u is a vector that tells you as a function of length along the vortex what the shape of the vortex is. So that is what is appearing here. So the first term in the equation is essentially the bending term associated with tension. And this calculates the curvature of the vortex and multiplies by the energy cost of bending it. This second term is the Magnus force that I talked about earlier. du dt is the local vortex velocity, and that minus the ambient superfluid flow determines the relative motion. The cross product of that with the vorticity vector times the superfluid density determines the Magnus force per unit length that is on the vortex line. But then we should add in other forces, in principle, a non-dissipative lattice force, just what is the force between each of these nuclei and the vortex segments. And then finally, because we expect some kind of dissipation associated with motion with respect to the lattice, I put in just a linear drag term for illustration, though this could easily be generalized. So I put in a drag coefficient, just 1 power of the velocity. So this...
Does the dissipation vanish in certain limits? If it was at 0 temperature, would there be no dissipation?
I think, no, for the exchange with lattice phonons, for example, that would occur even at 0 temperature. In fact, I'm I'm really operating at 0 temperature here. I'm not considering thermal excitations in the vortex core. These things, such as dissipation, whatever it is, could in principle depend on temperature, but I think will be finite at 0 temperature when you're discussing energy exchange with the phonon.
We're just creating phonons, you're saying?
Heating lattice phonons?
Well, something or the other.
Yeah, do you interact with the superfluid phonons?
Oh, that is not included here, and this is something we should discuss with Sanjay. This, in principle, I think this could model that as well. Then we might need we might need a different velocity.
I think, yeah, so the question is whether there's a drag term for slow velocities. And it's not entirely clear if there is such a drag term for very low velocities, even for creating lattice phonons. Well,
It turns out that this term will not matter for what I'm about to say. So the fact that I've assumed that it's linear and I'm taking this drag constant to be a constant is completely irrelevant to what I'm about to say. This equation has some interesting properties. If you were to throw away these terms and also Vs, notice what we have is a diffusion equation with a cross product in it. So this will support diffusive waves. There's no inertial term. It's just diffusion. And because of the cross product, which is due to the lift nature of the Magnus force, the excitations will be helical waves that travel along, circularly polarized waves that travel along the vortex. These are called Kelvin modes, and they were worked out by Thomson, Lord Kelvin, back in 1880, before they knew there were superfluids, and I love to reference him to have this work that's so relevant to the dynamics of these quantum liquids that we're now trying to understand. It was an important paper, I would say. Also, the vortex...
It says diffusive, but you somehow say these are real frequencies, right? Is that just because of the cross product? Yeah?
Yes. Yeah.
So it's not really diffusive.
Well, it's diffusive in that we have waves that propagate along. They have a frequency, but the wave packet will spread.
Yeah, I mean it's more like free particles than the energy going like k squared. I mean, apart from logarithms.
Yeah. Because of this cross product, this lift nature, the drag force, the vortex tends to move transverse to any applied force. So if I put a nucleus here and a vortex here, the vortex doesn't go straight at the nucleus. It tends to orbit. So there's some rather unintuitive things about the nature of the force. Also, this is a first order equation in time. Derivative, there's one derivative of the displacement. And so the velocity of the vortex, not its acceleration, is determined by applied forces. So this is not like a massive particle. So the state of motion will depend on the position and the potential. That is, the velocity will depend on all forces on the vortex, unlike a massive particle where velocities determine accelerations. Here's some simulations that illustrate some of the complicated dynamics that occurs if you put a vortex into some sort of random potential and try to move it through. So suppose we have these nuclei and we now impose a superfluid flow, a net superfluid flow like this, and ask what this does. And the way I addressed this problem was I just put down nuclei randomly for convenience, just in case the crust is amorphous, but even if it's not, we have some crystalline structure. It'll almost never be the case that locally a crystal is perfectly aligned with the rotation axis that a vortex tends to follow. So I think if you then take, say, this microcrystal and rotate it a little bit, and now thread that with the vortex, a random approximation for the distribution of nuclei should be a pretty good one. So I did some simulations where I took a big box, put in many nuclei, 50 zones, and then had periodic boundary conditions on the vortex line and solved the previous equation of motion that I showed for the motion with parameterized vortex nuclear potential.
So
this
3D box or 2D box?
I'll explain what we're looking at. So the vortex is coming out of the board at you guys. We're looking in the XY plane, and this is an example plane containing nuclei indicated by the circles. Now, I just made the circles big enough so that you could see them. These are not overlapping nuclei. They're just two nuclei that are close to one another, because I plopped them down randomly. So then the superfluid flow is to the left in this picture. The vortex is coming out of the board, and we're looking at what a segment indicated by the red curve is doing as it moves along under the influence of this force. And I just have some velocity here in some units. So what it does is it starts here, and it moves around, and it starts doing some of these loops, because as it's moving along and trying to orbit these nuclear potentials, the same thing is happening above and below at all levels. Go up a lattice spacing, something similar is happening with a different distribution of nuclei, and the whole system is coupled to itself by tension. So these helical waves get going along the vortex, and we get these wiggles and jiggles as it moves along and gets excited by the nuclei at all levels. The motion is really quite nonlinear and complicated, but basically it plays a kind of pinball with the nuclei, but generally moves left with the superfluid flow being deflected by these nuclei. And this is with no dissipation at this point.
So if I had a simple question, because the force is transverse to the velocity, right? If I just had one vortex trying to interact with a nucleus, you would never really get pinned on it. Right? If it moved
That's
to
right.
it, you would always try to avoid that.
What would happen is, if I take the nucleus here, and we avoid now the complexities of the vortex having tension and exciting waves and so on, just take an infinitely rigid vortex, throw out the tension term, put a nucleus here, take a vortex segment here, there is a force on this vortex that immediately tells me what the velocity is. And that velocity is, if the nucleus is here, that velocity is in the transverse direction. I let go of the vortex and it simply orbits. It is effectively pinned. It is pinned in that orbit. If I put a drag term in, it'll spiral down and stop on the nucleus. Then if you make it repulsive, very interesting things happen. It's still trapped. If it's repulsive, it is still trapped. It doesn't push away, it orbits in the other direction. If I put in dissipation, it'll migrate outwards.
Can I just ask, you've done a 3D
Yes.
simulation here, so these are projections of all nuclei you have?
No, this is just, I took a slice through one plane. For convenience, I established planes separated by a lattice spacing, and in each plane I put down nuclei randomly. I'm showing you one plane.
Yeah, the real,
It looks similar in any other plane.
is going to have some correlation lines. You can have a microcrystal with some size, some orientation, and the size of the crystal seems to be relevant if you want to figure out the strength of the pinning or the.
Absolutely. You can,
So,
because
I mean, to
that link scale.
decide that from one lattice plane to the next is completely independent, random positions is very extreme.
Well, if I want to take a regular crystal, and I thread a vortex through like this, and it's going to take some shape because it strikes a compromise between the energy gain of getting close to a nucleus and the cost of bending the vortex line. I mean, how different is that really from basically a random distribution of nuclei? I don't know. I mean, the next step could be to put in definite symmetries, but this is my starting point.
Yeah, I think.
I don't think it's going to matter much.
Well, the planes are strongly correlated. So.
The planes are strongly correlated, but what the vortex is definitely not going to do is it's not going to do this. It just costs too much energy to take those bends.
Sure.
It's going to tend to stay straight. Okay, so then if I am not along any lattice plane, I think that's almost like being random.
I I mean, you could find configurations where it pins every third plane or every fifth plane, or something like that. Seems to me, you have random orientations of these little crystals, one crystal will be just right, or the flux tube could bend slightly to.
I think that could be. The relevant correlation length, that is the length scale over which I can bend a vortex under its tension and stick it to a nearby nucleus, is say 50 lattice spaces. Well, that seems small. I think what you're saying sounds reasonable. But I think that it won't affect the basic conclusions that I'm about to tell you, which are shown here in the right diagram. What I've done here is I've turned down the velocity to a smaller value, the ambient superfluid flow to a smaller velocity. And that shouldn't say nucleus. There are no nuclei here, because what I've done is I've averaged over the length of the vortex and just taken, in this simulation, the average vortex location. What it does is it just doesn't move. It wiggles around the average vortex location. The length average position of the vortex changes, but basically this is trapped in a unit cell below this critical velocity. And that's true even with zero dissipation, which is a point I want to emphasize, is the vortex is pinned, even though it doesn't grind to a halt and is moving around, it's basically confined to a unit cell.
Is there one nucleus in that picture, or is there?
Cross this out. Cross this out. This is one plane. Here I've averaged over the entire length. And this is the center of mass, if you like, of the vortex. It's wiggling around in the simulation. There are no nuclei here. I'm showing you the entire length average vortex position.
If you really have no nuclei, what's pinning it?
The nuclei.
It has nuclei in all
Oh,
planes.
there's not showing nuclei.
There would just be, if I showed you a projection of all of the nuclei, there'd be a hell of a lot of circles in this. It would be confusing.
These cleverly chosen those to be marked by white circles.
They're the white circle, yes. They're the white circle. One right here.
That seems very Scandinavian.
So how fast is the vortex moving in the left picture? What are the units? What was this 2 times 10 to the minus 2? What are the units? How long is what is the going from one end to the other? What is the speed of the vortex?
The relevant numbers, well, finally when I convert, what I did here was I worked in terms of time scales of the basic unit of time is the time for a Kelvin wave to traverse one lattice spacing. And the basic distance is the lattice spacing. So I'm working in dimensionless units to define velocities in that way. But translated into CGS units, this amounts to about 10 to the 6 centimeters per second. It doesn't matter what the number is for this illustration, just I'm trying to emphasize that below a critical value, so I'm going to go in a factor of 20 times lower, the vortex can't translate along as it's doing here. It just gets
what is the speed of the vortex now? If I go from the end of one end of the red line to the other and divide by the time, how is that compared with your 2 times 10 to the minus 2? I mean, is it on average moving with the fluid?
Yes.
Or
yes. On average, they're very close to one another. Yes.
But how does the critical velocity relate to the number density of your nuclei?
I think I'll answer that question in a moment. If I don't, ask it again.
So are you saying you've got the analog of Anderson localization here, or
I didn't say that.
It's not moving anywhere?
Yeah, it's that way.
The vortex it's moving, the individual segments in this right picture, they're wiggling around within each unit cell, but overall there's no translation.
It's not moving
right, there's no translation.
So so you have random distribution of pinning sites, right? The nuclei, and but there are 2 limits to that. One is some kind of actual crystal limit, where it's uniform, and then the other limit is just really uniform density, in which case there is no force.
Yes.
Right? And so this have you seen if a regular lattice, in a regular lattice, there is no such localization? And it's the randomness that's actually leading to this localization.
I've not done regular lattices yet. That's hard.
So then maybe, you know, what Chris is saying is that, you know, it's the random lattice that's localizing this.
Yeah, I mean,
Yeah.
that's what
That's
it looks like.
localization.
Are they pinned by impurities and defects in the lattice rather than in the lattice?
What was the last word in your sentence? Are they pinned
Are
by-
the vortices pinned by the
Oh.
defects and impurities in the lattice rather than the lattice itself?
I think that I maintain that it's not going to be changed a lot by having a regular lattice, just because we have a potential whose characteristic length scale is the inter-ion spacing, for which we have a force that is about an MeV over about 10 Fermi. I think those are really the only relevant quantities that determine this localization of the vortex. So if we put in a regular lattice, I think what it might do is if you choose some favorable crystal planes, it just becomes even more strongly immobilized. So I do not think this is an artifact of this randomness with which I put down these nuclei, because I've experimented with putting these down with different distributions, and it doesn't change this basic result.
Well, it might be fun just to put in a regular one.
Yeah, yeah, I can certainly do that.
Because I mean, it presumably depend also on how bent up your vortex was when you put it in. If it was fluctuating enough, then it would overcome these little ups and downs in the lattice.
Ideally speaking, if your lattice were perfectly regular, you could change that motion to a perfect circle, right? If you pin
Oh yeah,
along
sure.
the same
Yeah,
axis.
that's a good point. That's a little, I think a little arbitrary, but interesting. If we just took
Yeah.
a single, that's our lattice, a single lattice, and we put a vortex line here. The type of localization in this case is that it will just orbit this array at a velocity that's determined, or at a frequency that's determined by the force per unit length, and the distance at which I place it. If I put it very far away, it is still trapped, it just orbits in a larger circle. If I put it very close, it orbits very quickly.
And if the spacing is not regular, then you would have a drift.
No, there's no.
Well, because the force would be position dependent, and so you would have. I mean, it's typical.
You have exactly this, and you have this. If it's not regular.
If I'm saying if you're, if x is your horizontal direction, and you have that the spacing in x is not constant, okay, then you would have drift in that direction.
If what is not constant?
So now imagine you have lots of these in the x direction. Okay.
So we'll call this the x direction.
Right.
Okay.
And allow for the density along the x direction to be non-uniform.
Oh, so we're changing the lattice. The lattice
Then you
density.
would have a drift. You would have a rotation. I mean, it's like charge particle drift.
Yeah.
Because the vortex is position dependent.
I think so. I think though that these localized forces are so large. Imagine that's a very slow drift.
It would be, given by the length scale over which.
So how many, on average, how many pinning sites are there per unit length of this vortex? I mean, in this simulation, do you?
The bending. So far, we don't have pinning in the sense of the vortex stopping because I've not put in any dissipation. So let me show you that calculation next.
Bennett, excuse me, do you understand the transition between one and the other? What is the nature of the transition? Is it very sudden, or
Yes.
as you increase VS?
Yeah, I'll show you that result too. It basically, a lot of the parameters of the potential and of the vortex itself just scale out of the problem completely. I'll show you how that works in just a moment.
So if you treat the drift velocity as a function of this VS, external VS, is there a jump?
Yeah, pretty much it. A very sharp transition. I'll show you that.
It's percolation effect, something like that, and more or less
Any further discussion on this?
Well,
I got this slide
yeah,
to
to 7 p.m. So
We're through the first 55 minutes. Okay, let's put in dissipation, and again, I'm considering an example segment like I did in the previous picture. And in fact, the starting point here, the red line is for the somewhat higher ambient superfluid flow. This is the curve I just showed you. It basically translates with the superfluid approximately at the superfluid velocity. But if I put in some fairly strong drag, what it will do is it will damp to a position which you'll notice doesn't coincide with any nucleus. And that's because of the very high self-energy of the vortex, it can't get right onto a nucleus. It can get close to a nucleus locally, but it strikes the best compromise between the cost of bending and the gain of getting close to the nucleus. So this is only in one lattice plane. We come out a lattice plane, it's say over here. We go down a lattice plane, it's say up here, and there's some curviness to this now pinned, immobilized vortex. And that basic length scale for the pinning, so I've been considering a random lattice, but we'll have the vortex, say, getting close here, and put a nucleus here, it gets close to this one, and it just threads in some way which minimizes the energy. And this basic length scale, this correlation length along the vortex, or L bend, say, is approximately 50 times the lattice spacing. And so that is the basic length scale above which you can think of the vortex as becoming flexible and able to get close to the nuclei. Before that, it's very stiff and it has to bend at some cost.
So are those two curves with and without drag, or for different superfluid velocities?
Oh, I'm sorry, I misspoke. These are both with drag. This is a higher superfluid velocity. It moves along, even with the drag, it keeps going at nearly the superfluid velocity. And then, as I reduce below a critical value for the velocity, it just grinds to a halt.
But that was very similar to what happened without drag also, right?
Yes, however, without drag, it never stops. With drag, it stops. But
the velocity is drag independent.
The velocity,
The critical velocity is
yeah, the critical velocity is drag independent.
But is it density dependent? That was my first question. Does it depend on the number of nuclei you have?
What I have here is I have a constant, though the nuclei are randomly spaced, I've assumed a density for the
Yeah.
nuclei.
Oh, you change it. You have twice as much. Would the critical velocity change?
Yes. Yes. it would.
But
Do
this
you have
red
random
curve, is
spacing
this the
in
same
Z?
as the previous red curve? without
Not
drag?
exactly. I miss. Not exactly.
Well, it looks
Well, now I guess it is exactly. I guess the curve I want you. I guess the curve I want you to focus on is the black curve.
No, but I want
which
to
just
understand
moves.
why dissipation's doing nothing to the red curve.
I think all I did was put on the wrong line. I think you're right. It's exactly the same. I think what I did was put on the line. I will say the line with the drag that I considered, which stopped this vortex, changes this trajectory very slightly, but not much. I just put on the wrong line. It doesn't change it much. But basically, it still travels along at the superfluid velocity, above this critical Vs.
Because when it's doing that, it's quite heavy.
That's right.
There is no
That's right.
dissipating force.
That's right. That's right. The other forces in the problem dominate over the dissipation. So here's the existence, the transition to pinning that Yuri was asking about. We can define a couple of dimensionless parameters. One is a sort of strength of the vortex nucleus interaction in units of the vortex self-energy. And another one is a reduced drag coefficient also dimensionless, which is the ratio of the drag coefficient to the superfluid velocity times the vorticity quantum. And if you define these parameters, we measure the drag that way. So I'm just comparing two cases of absolutely zero drag and then a rather large drag. And this is a plot of vortex speed versus the ambient superfluid flow speed, but scaled by a factor of s to the -3/2. If you make that scaling, it turns out you can put everything on the same plot. And so if we had a free vortex, it would move at the same speed as the ambient superfluid flow, and that's what this dotted line of slope 1 is. Now, if we solve the problem and we let the vortex bounce around along the nuclei but have no dissipation, we have the blue curve, and at about, in these units, a flow speed of order unity, it just plummets and the vortex stops. And that was the trapping of the vortex with zero dissipation that I showed you. If, on the other hand, we turn up the dissipation to a rather large value, but not so large that the vortex is actually stopped by the dissipation. If I make the dissipation infinite, the vortex just can't move at all. It's in molasses and can't move. But if I give it a rather large value, such that it can still move, we have basically the same transition to pinning where the vortex stops. So the point of this slide is that the entrapment of the vortex by the lattice is essentially independent of dissipation. We do not need dissipation to stop the vortex and pin it. Vortices can pin to zero dissipation.
You tried the repulsive interaction.
Yeah. Yes, I also tried this with repulsive interaction. I took all of these and just flipped the sign of the interaction, and everything looks essentially the same. So that's actually an interesting point, because as we'll hear about related to pinning later, at some densities the vortex nucleus interaction is repulsive. And those regions have been typically thought of as places in the inner crust where pinning cannot occur, because the vortices will prefer to be at the interstitial points in the lattice, and they're far from the potential where the force is weak and the pinning will be weak. However, if the basic length scale of the potential is comparable to the lattice spacing, flipping of the sign of the vortex nucleus interaction basically has no effect. You're just taking this random potential I set down and turning it inside out, and you get pinning that's essentially as strong. And you get this same transition to pinning whether I switch the sign of F or not. A nice robust result.
And this self-similarity S to minus 1.5, is it possible to understand it in simple terms?
Yes. Yeah, it's basically, really what it comes down to is just comparing terms in this equation when you're at low velocities, and therefore approaching pinning, this term is negligible. And if the vortex is stopping, then, well, we throw away all these derivatives. If we neglect tension, it's basically a comparison between rho s kappa vs and the non-dissipative lattice force. And all of the scalings follow from that.
So what
It's basically F naught is the only relevant force in this problem. That is what is determining the pinning, the non-dissipative contribution of the force from the lattice. The drag just doesn't occur.
So what is the closest distance you find when it finally stops? You drew that picture on the far left where you had the vortex not quite on the nucleus, but at some distance. What is the typical distance scale compared to the size of the vortex and the size of the nucleus?
It's, well, since I assembled a random lattice, those numbers are almost random, and that some of them come quite close and others are quite far away. But I would say on average it's some fraction of the lattice spacing, say 25% of the lattice spacing. So getting comparable to the vortex coherence. But that's where the pinning occurs, is when you're getting the nucleus into the vortex.
That's what I'm trying to figure out, whether the energy difference between a vortex on a nucleus and a vortex very far away, whether that energy difference has anything to do with the force that you're calculating, that you need in this simulation. Because this is at some finite distance from it, right? So just calculating what's the energy difference between vortex and a nucleus at the same location, and very far away may have nothing to do with the force at some intermediate distance.
Yes, so what I had, because the form of that potential is not known, I had to model it. So what I did was I assumed that the force that the Milano group provides us with has a characteristic length scale that's comparable to the lattice spacing, which is also comparable to the vortex dimension. All these length scales are comparable, and I just modeled that interaction. I also played with different shapes for that potential, and it doesn't matter in these conclusions. It's all determined by energetics in the end, and by force balance.
But this force between the nucleus and the vortex is because the core of the vortex is normal, or is it because the superfluid in the flow has to go through the nucleus?
Well, there are different contributions. I think and Nico and Francisco can explain it better than I can, but they can correct me if what I'm saying is wrong. It's just that the vortex core is normal, and it destroyed the superfluidity to lower the system energy overall, the fixed angular momentum. The nucleus being at higher density than the ambient medium is because of the density-dependent gap, in a sense, less superfluid. But the vortex has paid the price of going normal, so by having overlap, I lower the energy.
That's the old argument.
So that's one contribution. Is that the main effect?
Well, this is a way of, an easy way of thinking, but as I will show, other complications could come out. But, well, I would say this is the general wisdom.
Okay, so we'll hear about that. As moderator, I think we should move on. Chuck?
If that MeV per nucleon, or per nucleus, were a tenth of an MeV, or 10 kilovolts, or 1 kilovolt, how small would it have to be before the picture changes?
Well, these scalings still hold, but certainly I think certainly by the time we get down to a vortex nucleus interaction that's comparable to the temperature, say 10 keV, then there's no point, you lose everything. Thermal fluctuations would just let everything move, and I think it would probably happen at a somewhat higher interaction energy. But if we take an MeV per ion and bump it down by a factor of 10, it doesn't change things so much. We still get the I'm doing all these calculations at zero temperature under the assumption that that energy is high enough as the calculations indicate that I don't have to worry about thermal excitations. That I'll worry about later, next hour of the talk.
So, but may I ask a stupid question? So this picture is for a given density of the nuclei, right? And if I were to imagine you have a different setup where you have very sparsely populated nuclei, all of this would essentially move to the left, right? The cutoff would move to the left because I would have would have no pinning whatsoever. There would be no critical velocity. And if I instead have a lot of nuclei, I would have the cutoff moving to the right. I would need very high velocity in order to see this. Now, if I am inside a star, a neutron star, I have this density stratification. So I would expect that the cutoff, the critical velocity, would be dependent on the position in the star. So
yes, it's
how do I
density
picture
dependent.
this? How do I picture this?
It's density. It is density dependent. It comes in right here through this factor S, and then eventually you convert these. I'm working with dimensionless velocities here, but you convert to CDS units and get some value. But it's basically coming in through this scaling S. So if I want to go to a lower density, where this interaction is of lesser strength that affects this transition in terms of an actual value for the velocity through this factor S. But then, when I make the final conversion, the lattice spacing comes into the conversion to a real velocity. But yes, if I go down to a dilute lattice, the thinning becomes very weak. And the critical velocity in real units, which will still have such a transition, but that critical velocity in, say, CGS units will be small.
But if I picture myself what happens to a vortex tube inside the neutron star, should I imagine that low density is free and then it's thin as I go towards the center?
Roughly speaking, yes. It'll be,
It's around the equator.
yeah.
Well, it's not just the equator; it's the density. The
It
equator you
goes
might have.
from the north to the south, so the north is low density. The
Yeah, but on the
equator is
equator.
higher density. Then
So when you, if you pin it in the high density region, and then you say you can move freely in above, then you would get bending costs on a global scale eventually.
Yeah.
But
So
you got the supercomputers.
here's
Take a larger sample.
an expanded view of the cross. The pinning force per unit length will be largest here and go down with density as we get out here. Since I put in many other vortices, however, when you have many vortices, there's a certain rigidity to many vortices in a lattice, that even if these segments are effectively free, the whole thing can't bend under the influence of the ambient superfluid flow, and basically it's the strength of the pinning in this region that determines how strongly the entire vortex lattice is pinned.
Bennett, in the blue curve, this individual fluctuations, is it just because you're simulating for one vertex?
Yes,
So if you
and I have finite size effects and so
so
on.
if you averaged over many vortices, will you
Right.
get something like a square root?
Yeah, I did some very longer simulations and beat down those wiggles, but those wiggles are basically numerical noise from just doing a finite size simulation. These are actually fairly big runs because I divided the system up into 100 cells, and I have to solve 200 extremely stiff coupled differential equations throughout the system to simulate this dynamics.
Stiff is stiff.
Be careful what you ask.
Some sarcasm coming
Well, I
over
said,
there.
that's it. You've shown us what a supercomputer, so he can do it.
It's what? The what?
You've shown us what a supercomputer, he can do the big one. Just pile it on.
I did it on this, it made it very hot. He's
So
got carrying
that
along
was
with
the-
fans running for days.
That was the pinning energy running to heat.
That was the dissipation. So, as a number, people have been asking what's the number, is that for the densities in which the Milano group would tell us we have pinning, because of the density dependence, we have some range for this critical velocity. It's about 10 to the 6 to 10 to the 7 centimeters per second. For the relative flow between the superfluid with respect to the pin vortices, beyond which the pin state is unstable. That is, they will unpin. We're on the other side of the transition. So then so that's angular momentum you can store in the crossed, available for glitches, for example. So if you just do that integral and calculate the angular momentum.
Bennett, this was a huge number.
Yeah. This?
Yeah.
Yeah.
10 to the 7 centimeters per second.
It's large. I agree with you. So that makes for quite a nice angular momentum reservoir.
So this corresponds to what spin? Relative spin between superfluid.
That is the relative speed. All velocities I've been quoting
Yeah,
are in
so
the,
this
in the
is
front of
relative
the solid.
spin of 1 hertz or something.
So there's a lot of angular momentum that can be stored with those high velocities. And it's about enough to drive giant glitches, but then you need a trigger. Just as a side point, how could this be triggered? Sudden heating has been discussed, turbulent transitions, and instability related to R modes, which I think Kostas is going to talk about later. So the third part of my talk, the relevance to neutron star modes of this pinning effect. I'd like to take as an example one of my favorites, just free precession, which we think has been observed in a number of objects. And just to remind you from classical mechanics, free precession or wobble or nutation is a rotational mode of the system that you get when you take an object with some rigidity and a symmetry axis, say an oblateness epsilon, which I'll take to be much less than 1, and I set this thing like a plate rotating about some axis which doesn't correspond to any principal axis of inertia. And what precession is in addition to the wobble, there's for an oblate object a slow retrograde roll about the symmetry axis in this direction at a frequency which is this oblateness times the angular velocity, and that's the precession frequency. In the body frame, which might be a better place to think of it, now aligning ourselves with the symmetry axis, what you see is both the conserved angular momentum vector and the angular velocity vector move in circles about the symmetry axis at this slow frequency epsilon times the rotation rate. So if we had a neutron star, a rigid neutron star of oblateness epsilon, its precession frequency would be epsilon times the spin rate of the crust, and the sorts of deformations that we talk about in various contexts from precession to gravitational wave emission involve oblatenesses that are very, very small. And so this precession frequency should be much smaller than the spin rate of the crust. But back in the 70s, Shaham noted that for a fluid plus crust, a superfluid that is, with perfect pinning, that is, if I just immobilize the vortices perfectly to the crust and don't let them move at all, that this result gets altered from the classical mechanics result. We get, in addition to epsilon, an increase in the precession frequency, which is the ratio of how much moment of inertia is being pinned to that of everything else, basically I of the moment of inertia of the star. Well, if you're pinning through, say, the entire inner crust, that's 1% by moment of inertia of the star. That could be 10 to the minus 2. Or if we're pinning throughout the core, say due to vortices pinning to flux tubes, then this ratio could even be, say, as large as 10, or even a bit larger. In any case, this precession frequency, once we have pinning, is a much larger fraction of the angular velocity of the crust, and the period becomes, in either case, less than a minute, rather than the years that has been inferred from, say, this precession candidate, 1828 minus 11. So if we have perfect pinning, we have a bit of a disaster in trying to explain long period precession over time scales to years. It's effectively a gyroscopic effect that makes the precession very high frequency. And this in particular it'll challenge some of the notions we have about, for example, the outer core. If we have flux tubes, I've drawn a tangled mess of flux tubes and a nice rectilinear array of vortices. The vortices I mentioned are expected to pin to the flux tubes with energies of about 5 MeV per intersection, but the flux tubes are extremely numerous compared to the vortex lines, even for a 10 to the 12 Gauss neutron star. Then, if we try to change the angular velocity of the neutron superfluid in the core, we encounter this fence of flux tubes, but the flux tubes, being in a superconductor, are really frozen to that liquid, and almost frozen. It's determined by the conductivity, but it's very large in this superconductor. And so these flux tubes are pinned to the vortex lines are pinned to the flux tubes and vice versa. It's like we've inserted a giant gyroscope into this thing, and this thing will precess very quickly at the spin frequency of the object or higher. And so you can begin to ask, as I did, what part of this picture is wrong? But pinning will not be perfect. And if you take a vortex segment and you put it in some distribution of nuclei, thermal activation will allow this vortex to hop through the potential and move along. So these vortices can creep through this thermal activation process that's been estimated in some papers, and the vortex velocity will be some characteristic velocity times an activation probability. A is the activation energy required to unpin a vortex segment, and T is the temperature. And then it will move, not necessarily with the ambient superfluid, but in some different direction. The vortex velocity shown here. So in this picture, basically the rotation axis is like this. I have an ambient flow like this, and the vortex is now taking some direction not exactly parallel to the ambient superfluid flow, and is moving somewhat into the board, away from the rotation axis. At some angle theta d, I put d here to indicate this is determined by the dissipation. I'll call this the dissipation angle. And so it'll take some velocity, some unit vector associated with whatever this whichever direction VV is pointing. So in creep, the speed, the magnitude of this velocity will be much less than the ambient flow. So it just stays put for a long time, then it hops to a next possibility for pinning, and then it hops again. And this is dissipative, and one can show that the dissipation rate is related to the dot product between the vortex velocity and then the cross product of the superfluid velocity of the ambient flow and the vorticity. And this, it works out, is proportional to the sine of this dissipation angle. So if that dissipation angle is zero, it's moving in the direction of the superfluid, though slower. There is no dissipation whatsoever associated with creep. On the other hand, if I consider the opposite limit of it moving exactly transverse to the superfluid flow, which is in the direction of the Magnus force, that is the most dissipative possible situation. And that occurs when the dissipation angle is pi over 2. But I was asked in this talk to emphasize what's known and unknown, and what is, though these speeds have been estimated, the direction of this vector and therefore the dissipation angle are unknown. And as of yesterday, Sanjay and I are planning to calculate this. I just want to finish with the procedure for calculating global modes. We've been talking, we spoke all last week about the difficulties of assembling an at all realistic model of neutron star seismology. We have to wonder about how the crust talks to the core, and what are the stresses that determine that, and what are the appropriate boundary conditions, and how do we handle the density dependence of everything. Well, one way to calculate global modes or precession modes is what Sedrakian, Wasserman, and Cordes worked out in '99, and that is to basically integrate over things that you don't know. So if you assume a friction force on the superfluid, they took a generalized form, and then rather than deal with boundary conditions, they did volume integrals to obtain the superfluid torque on the crust in the approximation that the superfluid is rotating with one angular velocity, therefore as a rigid body. So we're not doing hydrodynamics, though we are using forces coming from a friction force that are motivated by the hydrodynamics. This is certainly not going to give the final answer, but I think it's a good way to assess the effects that different assumptions for the friction can have when calculating modes. And then what you do is you linearize the system of equations that you get. You get Euler-like equations, which are not too bad to solve. So there are two modes of interest or two types of modes and two regimes that come out. If we have a high drag situation, which is what has traditionally been assumed, where this dissipation angle is near pi over 2, there's a very fast underdamped mode, and that's the mode that Shaham discovered in '77. There's a second, very slow mode, associated with the fact that we are now letting the vortices move slowly. But because the dissipation is so large, that mode is overdamped and just irrelevant to the system. It dies immediately. But a limit that has not been considered, which I think is very interesting, is the completely plausible possibility that the vortex creep is actually a low dissipation process. And what that means is that it moves along slowly at small dissipation angle, and I've done that mode analysis. There is still the fast Shaham mode, underdamped. There is a slow mode because we're letting the vortices move slowly, but because the dissipation is low, no surprise, this mode is underdamped. So we now have a long period underdamped mode, and that becomes interesting when attempting to explain long period precession. And when I talk on Friday, I'll go into some of the technical details of this mode calculation, how I did this and what I assumed about the friction and so on. So finally, to conclude, or nearly so, one critical question to understand related to neutron stars, I think, is vortex creep a low drag process or not? It could be. But if pinning is inevitable, as I tried to show in the middle part of this talk, we have to address this. And then we need to understand, because pinning won't be perfect, they'll be thermally activated through the potential. The vortices will move through thermal activation. We need to know when doing mode calculations just how dissipated that process is, and that needs to be calculated. To summarize what I've been saying in the dynamics section of the talk, the vortex mobility will determine how how the superfluid talks to the solid, and that is related to the hydrodynamic modes, but that's determined by the microphysics, and they're all tied together. So I think to make progress, we need a better understanding of the microscopic physics of vortex creep. In particular, we need to know at what speed vortices can creep under a given force and how dissipative that process is. We need to self-consistently include pinning and creep into hydrodynamic models that we're building. And a question I have, is pinning really inevitable also in the core? This energetics argument of a vortex line encountering a flux tube having an intersection energy of 5 MeV per intersection, I think a real calculation needs to be done, perhaps by the Milano group, is to, as you bring a vortex near a flux tube, I think both structures are going to be deformed. Is that 5 MeV per intersection, is that a realistic number or not? Is it too low or is it too high? And I think we need realistic hydrodynamic models of a star, and many of the people in this room are dedicated to working on that. Half this cast of characters is in the audience today. But I think we're at the point where this really needs to be pushed further, including this sort of physics, including pinning consistently. And that is it. Thank you very much. Less than 5 hours.
Yeah, but I wish to point out, you were complaining about Danny being an hour and 20 minutes, so you beat him.
1 hour, 22 minutes.
Am I the worst? am I the worst violator of the 50 minutes?
I think you now took over.
There were some questions.
That's okay.
Would you be upset if there were no superfluid in the core? No neutral superfluid?
If there's no, well, no. I would not be upset because back when I questioned this picture of, I said this situation leads to high precession frequencies. And I asked which part of this is wrong. Well, if we have, say, if we get rid of the flux tubes, then the vortex lines can move and we don't get higher frequencies from the core. Or if we get rid of the vortex lines, we can keep the flux tubes and avoid the problem that way. So, or both. Either one would evade this gyroscopic effect that tends to make the precession mode of very high frequency, and then you have only the crust to deal with. So one possibility is maybe we have normal superfluid. Take the superfluid of your pick. Maybe the neutrons are normal or the protons are normal, one or the other.
Right.
Then we don't have a problem of pinning in the core. We have pinning in the crust, which I'm arguing is inevitable, but then if creep is a low drag process, we could have long period precession modes if the dissipation is low enough. If this pinning picture is correct, we really need to understand what determines the vortex mobility against the flux tubes and how dissipative that is.
The reason I ask is that current estimates, or at least the most recent estimates of 3P2 gaps are very, very small.
Yes.
It could easily be 0.
Yeah. Mm-hmm.
And so that might help you.
Yeah, and I think that, well, those are the hardest calculations to do, and so that's where the biggest uncertainty lies, as I understand it. But that's the pairing situation for the neutrons is much more uncertain than that for the protons in the outer core.
And the question
Well, even the
also-
protons haven't been done that seriously.
No.
I mean, because the induced interaction is not
Yeah.
being properly taken into
Yeah,
account.
so this whole picture could be wrong.
In relation to this question, so how old are these processing pulsars? Maybe they're still warm enough that there's no neutron superfluid. And then later on, then superfluid turns on.
No, well, 1828, for example, there's nothing special about it. It's 10 to the 5 years old. It has a.
So
It
it's
has
still
this-
warm.
It's. Pardon me.
It's still warm in the cooling curve.
Well,
So if the gap is very small, it puts the machine when the neutron are not yet superfluid, and then
What is the core temperature? Ish.
10 to the 8.
Yeah,
This is it.
that's.
No, it's
What is
entirely
that
possible
average
that
mass?
So with a small gap. predicted by Hakim, could be normal. But then a little bit later, when you get a few
It is-
100,000 years old, then you become superfluid.
But Chris, the small gaps you refer to are in the core, right?
Yes, it should be too.
No, the
Well, they also extend into, what was it, the lowest KF was 1 within, then the lowest 1.
So now we're talking about abandoning superfluidity basically at any age because it's into the 5-year object. It's middle-aged at least.
Yeah, but at the end of neutrino cooling, it's getting into photon cooling, so it could still be warm enough at the neutrino normal.
Then
It would be interesting if you find a million years old pulsar which has precession, then it's more difficult to avoid superfluidity.
then we can ask Costas how we get a glitch in an object that's 10 to the 3 years old, 4 years old, and much warmer.
Come back to the question we talked about before, given that you need a 1.4% of the moment of inertia in the superfluid, now, will the crust superfluid be able to do that? And so that's something you could quantify, and if that's, the answer is no, then we will need something in the core.
Yeah.
So, we can constrain this better, hopefully.
There's one other advantage of having a very small triplet P2 gap. It reduces the number of fluid components you need.
Yeah, but we need as many as possible. The more the merrier. The other thing we I guess in this discussion shouldn't forget the question mark in the core.
Yeah.
And it seems to me inevitable. That whenever
Not to
you-
scale.
Yeah, exactly. That's
The
not
question mark is not to scale.
If you put that question mark in, and so suppose we remove the 3p2 neutron superfluid, the exotic components that you expect probably to be there in the question mark, then we're going in uncertain territory again. And those will not be 3p2 gaps, there will be 1s gaps again. Right, so I think we probably need to worry about this regardless. So I don't think just removing the 3p2 superfluid makes all my work completely redundant. Most of it, but not all of it.
But I thought Danny was suggesting that he needed a 3p2 gap when it was relatively in the neutrino cooling epoch to better explain cooling data.
Within the minimum cooling.
Yeah.
It doesn't have to be right. If you put anything else, then
Yeah.
if you have vanishingly small triplet P2 gap, then half of the young neutron star are incompatible with the minimum cooling.
That's right, the observations are wrong.
Observation will be wrong. Or it does say that half of the neutron star have something exotic, so this question mark is.
Do you trust the observers? No.
No,
Come on.
no, don't. They're all doing this conversation ways rather than photons.
I think that's
No, some measurements are relatively trustable. Anything
So
to be off by such large. Some are lousy, but some are.
More trustable than some theories.
That's some triplet P2
You only say that because you know the theory is better. So you know not to trust us, right?
Well, I'm sorry to go so long, but in my defense, people were speaking as much as I was, so 100 minutes.
Yeah, right. Right. Shall we have a quick...
The moderator says we should have a coffee.
I don't think it's going to make it smaller because it's not. I don't think it's understood. Because it's not very close.
Yeah, that's
Aber wie der Klassiker,
yes, could be completely classical, right? You cannot wrap it in random potentials. Coherent effect coming from random,
Yes.
coherent scattering. And this is a different effect.
The numbers.
This
the
effect
numbers
survives
I gave.
only for random lattice.
Yes.
It disappears. So you don't have to It's an analog movement.
Yes.
So I don't think it
So that was from your knowledge,
Yeah.
basically.
It seems like it's completely classical motion, of course, so it's just.
Right. Sure.
But I don't know about the
the strength of the interaction and the density. Yes.
Seems like a second order. If you think of
Yeah, it goes, it scales like the,
It's probably in a
the
simulation.
interaction strength of the
The
three
question is,
There's some kind of competition going on
between
with other things being fixed.
You just change that parameter and the centric, so it wants to deform the potential. And you manage that? So how many you many like spacing you
Put in 100 zones. 100 lattice space.
Because you said
periodic
you
interval.
you spoke correlation of 50.
Yeah.
So 100 is it enough?
I pushed, actually, well, I did different lengths. I think I probably, for the simulations, I indicated, I think maybe I tuned things so that that length scale was more like 10, and then I had 10 times as large a grid. And I did some other checks where I let it be larger and have the grid be, say, 300, and I ran that for days. And so I just tried it. Yeah, so until I was confident of that transition. Yeah.
That's very nice. Mira, ¿cuánto? Que no sí, mira, so
Perché anche chi è dopo quello del lungo? You are not the first speaker. You are the second speaker. Just to be sure. Yeah. Just to be sure. Well, I collaborate with Milano Pesco, but so you are also